Hello all of you. So in the last lecture we have discussed the idea of thermodynamic ensembles and taken the example of microcanonical ensemble NVE, and I also discussed like what are the other types of ensemble. So today I will do the discussion on the most common ensemble or most practical ensemble, that's called the canonical ensemble or the NVT ensemble, and I will show you that how can we compute thermodynamic properties using this idea of ensembles. So, as we discussed in the last class, a canonical ensemble has the number of molecules, the volume and the temperature as the control variables, and therefore, we can imagine the ensemble as composed of systems which are having a constant number of molecules, constant volume and constant temperature, right. So, when I say I can control this, that means I can do the experiment at any possible value of number, volume and temperature. So, all these systems in the ensemble are having the same number, volume and temperature. In total there are some A systems, right. Now, to visualize this, one can imagine that you have this A systems contained within some infinite heat bath. This is simply a theoretical construct to imagine like how this can be realized. This is not something that is practically done, right. You can imagine that you have an infinite bath, so that the system is very small in comparison to the heat bath, and temperature of the system is maintained by the surrounding, that is the heat bath. And we also assume that there is no interaction among the systems. Systems are far separated from each other, and the temperature of the system is maintained by using that heat bath, right. In reality, in a practical scenario, what we will do is like we will take these systems as different states at different locations of the system, or it can be imagined as a particular state, but at different time instants, right. The key idea is that the number, volume and temperature has to be constant, but the configuration of the molecules, their positions and momentum and the distribution of energy among the molecules can vary between different systems in the ensemble. So, since in this case NVT is being controlled, the other variables may change. In this case, unlike the microcanonical system, the energy of a system in the ensemble is not same for different systems of the ensemble. But now we are referring to energy of the system. When I was doing the microcanonical ensemble, I referred the energy as epsilon j, but that energy was the energy of molecule within a system of the ensemble. Now, I am referring to the energy of the system as a whole. But now I am referring to the energy of system as a whole. Right, energy of a system in the ensemble. So, in this case the index j is going from 1 to A, and in this case the j went from the possible energy state within a system, right. So, in the microcanonical ensemble, the energy of all the systems were same, equal to E, that is the total energy of system was same. In this case, the total energy or the internal energy is different between systems in the ensemble. So, now just like we had different states of energy of a molecule in the microcanonical ensemble, we can have different possible energy of the system in the canonical ensemble. So, just like we had energy levels for the molecules, now we can define energy levels for a system as a whole. The key point here is, since the energy of a molecule is discretized, so therefore, the energy of the system is also discretized Although as you increase the number of molecules, the discretization becomes very unimportant. We can assume as a continuous energy spectra, but nonetheless the energy is discretized. That is the key point that I am borrowing here. So, now we will talk about energy level spacing. So, that refers to energy of the system containing molecules, not the energy of molecules themselves. That is true for the canonical ensemble. So, now I can say you can have many possible energies, let us say E1, E2 to some EL. These are the energy levels of system and if you start with some A systems in the ensemble, we assume that the A is a very large number. So, for those systems, some of the systems will have energy E1, some will have energy E2 and so on, right. So, keep in mind that now we are talking about number of systems having that energy instead of the molecules. So, then we can write as the occupation number of energy levels. The occupation number means how many states has that energy. So, number of systems in ensemble having energy, let us say E j, and that I can define as A1 for energy level E1, A2 to some AL, right. And as I enumerate the systems in the ensemble, then just like the energy levels, the distribution of energy levels can also change. So, in total we are talking about some particular distribution of energy level, let me call that A. So, that A can change between systems in the ensemble, right. So, I am not even coming to the most probable distribution yet. So, we can pretty much have the ensemble comprised of all possible distribution. The only criteria we are putting is the number of molecules, volume and temperature are the same. So, in that case there is a whole range of possibility of the occupation numbers or the number of system in a given energy level, and that distribution I refer as A, right. We can again think in terms of the example I was giving you of say 3 quanta among 3 particles. The only difference here is that we are talking about 3 quanta among 3 systems, right. So, it is a more microscopic view than compared to what we have used earlier. But then you will see some similarity in the math nonetheless. So, just like we could distribute the energy levels in the molecule using certain number of ways, the same applies here, but for the systems, right. So, we can now say that for a particular distribution A, the number of ways of doing that is something like A factorial divided by A naught factorial, A1 factorial to AL factorial, or we can say that the sum over AJ factorial divided by product over AJ factorial, where now the summation and product is over systems. So, J is over systems in the ensemble, right. And we are hoping that A is really so large that we are able to enumerate all possible ways. Again, it is a theoretical construct, but it makes things easier to think of, like if we enumerate all the possible state, then these are the number of ways this can possibly happen. So, now if I am interested in asking the question, what is the average property of the system? So, then the average property is the average over all the systems in the particular ensemble, right. So, the way to think about it, let us say if I am interested in some property M and I want to find its average value, that property can be for example pressure or energy. Whenever in thermodynamics we talk about pressure or energy, it does not refer to a particular configuration, but an average over a large possible number of configurations, and in this case A is that large number of configuration. So, basically whenever we find an average property here, it is average over all the possible states in the system, right. So, one way to define that is that I can find the energy, find the value of m for any property m. We can find the property m when the energy of system is E j. So, m j is property m when the energy is E j and multiplied with the probability of that happening. So, P j is the probability of having energy E j. So, I am pretty much finding an expectation. So, I will write this as m j P j, but keep in mind that even if I do not put E j in the brackets, m j refers to the property value when the energy is E j. I am making an assumption here that it only depends on the energy of the system, right. So, for any given energy, just like what we had in the macrocanonical ensemble, even for the same energy you can have many possible distributions of the energy within the molecule. But in the canonical ensemble, I am not considering that. In the canonical ensemble, I am assuming that the property value is the same for a given energy E j of the system, irrespective of how the energy is being distributed. That will be valid for microscopic properties that are typically used in thermodynamics, right. So, the properties I am trying to do this for are the properties which I compute on an average, not the properties of individual molecules. So, with this kind of an idea, the question is how can we find the probability of having the energy E j, right, and that is clearly given as something like the number of states having energy E j, that is A j, divided by the total number of states in the ensemble, right. And what is this number? So, this number is going to change for every possible distribution, right. So, A j is not going to be constant, because you can imagine different possible distributions, and different possible distributions will have different number of systems having energy E j, right. So, therefore, I am interested actually in the average value of the occupation of the energy level E j, right. And how can I find that? Is I can basically list all the distributions, and for all the possible distributions I can compute what is the A j value for that distribution and divide by the all the possible distributions, right. So, what I am doing now is I am not even referring to only the most probable distribution. W A is the number of ways of having a particular distribution. If I sum this over all the possible distributions, that will give me the total number of ways energies can be distributed. Now, out of this, for W of a particular A distribution, you have A j ways in which we are getting energy level of E j. So, if I multiply W of a particular distribution with A j, it gives me the number of ways in which A j is happening. Now, if I sum this over all possible distribution, I am going to get the total number of ways for all possible distribution. So, if basically the probability is the number of ways in which an outcome is possible divided by the total number of ways. If this confuses you, you can imagine that the number of ways is proportional to the probability, right. So, whatever is appearing here we can think of as the normalization of probability. So, if I divide the W A by sum over W A, essentially what we are getting is the probability of getting a particular distribution A, right, and I am multiplying that with the value of A j for that particular distribution. This is what we are doing. So, now clearly if I start listing all the possible distribution, this becomes a very untraceable problem, right. It is very difficult to even think of all the possible ways of distributing something. For a smaller number of quanta we can, but if we are thinking of a system as a whole, then the number of quanta are huge, and therefore, it is not quite easy or even tractable to think of all the possible distribution, right. So, we can simplify this problem by assuming that we are already in the most probable distribution, and this is a great simplification that we can do, because in any case we know that at equilibrium the distribution should be close to the most probable distribution. We made that argument somewhat logically earlier, but we also demonstrated it for coin toss examples and so on. So, even though other distributions are possible of the energy levels, the most probable distribution is the one that is happening in most of the cases, and therefore, instead of summing over all the possible distribution, we can sum over only the most probable distribution, and that greatly simplifies the way we are doing it, right. So, the assumption that we will make is we have the most probable distribution, that is I am looking at now a particular distribution, let me call that A star, which corresponds to some values A 1, A 2 to A L of the occupation number. Let me put them also star to indicate that this is the occupation you have of the energy state for the most probable distribution. So, now I am assuming that all the systems in the ensemble they can have different energies, but the distribution of the occupation numbers will follow the most probable distribution. So, if I do that, then I can write my P j, that is equal to average A j by A, as now it is no longer sum over all the distributions. Now, we are only doing it for the most probable distribution. So, we can compute the number of ways for the most probable distribution and compute the A j value for the most probable distribution. Now, we are no longer doing the sum, because I have already assumed the distribution and divided by, again we had a summation, but since we have assumed the most probable distribution, I have removed it, and therefore, these two will cancel, and what we are left with, there was a 1 by A here, is A j for the most probable distribution. Let me write as A star divided by A, just like what we had earlier. Keep in mind that there was a 1 by A also appearing here. So, now if I do that, then the problem comes down to how do I find the A star or the most probable distribution, and this we can do in the same way we did for the microcanonical ensemble, with slight difference in the equations, because now I am talking about energy of systems instead of energy of the molecules. So, the problem now is we need to maximize W and that is equal to A factorial divided by the product over A j factorial, and I am doing it all for the most probable distribution. So, I will put a star for the time being. Actually, we are going to so, we are doing it for the most probable distribution. So, when I minimize this function, I will get aj star values. This I can write as summation of aj factorial by product over aj factorial. Keep in mind that both the summation and the product is over different systems in the ensemble, which are assumed to be in the most probable distribution. That will come later after we do the minimization. So, this we have to maximize for the aj values for the most probable distribution. So, instead of maximizing this, we can maximize ln of w, and ln of w is given as ln of aj factorial by product of aj factorial, which becomes and by more or less same argument we had for the canonical ensemble, we can approximate as summation over aj ln of summation over aj minus summation over aj minus summation over aj ln aj plus summation over aj. Again we have the cancellations and we have this particular value of ln w. And now, just like what we had in the macro canonical ensemble, in this case also we have two constraints. The first constraint is summation over aj is the total number of states in the ensemble, right. The meaning of the terms are different, but the equation looks identical to what we had for the macro canonical ensemble. Now, we are talking about distribution within the systems as opposed to distribution within the molecules. So, this is equal to 0, and then again we have for the energy, and the key point here is that this epsilon is the total energy of a system, total energy of the ensemble to be precise. And the way to think about it is like, although we have assumed that the systems have different energies, that is placed in an infinite bath. So, if I take the system along with the bath, that becomes a system that is isolated, right. So, for the entire ensemble, we may assume a total energy, because there is nothing outside the ensemble, right, because that systems plus the bath included must have some total energy, and that we can assume to be constant. Other way to think about it is, if I simply add over energy of all the systems in the ensemble, that should be equal to constant, and that I call as capital epsilon, not the same as small epsilon what I had earlier. So, now the problem is, we can write the maximization as dou ln w by dou aj minus again some Lagrange multipliers, let me call it lambda 1, dou g1 by dou aj minus lambda 2 dou g2 by dou aj, that is equal to 0, and ln w we already have found is equal to summation of aj ln summation of aj minus summation of aj ln aj. So, if I do this derivative with respect to aj, what I will have is, using the same kind of math what we had for the canonical ensemble, what we get is this, which is minus ln Aj by summation over Aj, and I can find the dou G1 by dou Aj and dou G2 by dou Aj in the same way more or less. So, G1 is summation of Aj minus A is equal to 0. So, dou G1 by dou Aj is equal to 1, and G2 was Aj Ej minus capital epsilon is equal to 0. So, dou G2 by dou Aj is equal to Ej, and therefore, what we have is minus ln Aj by summation over Aj minus lambda 1 minus lambda 2 Ej is equal to 0, and therefore, we can write Aj by summation over Aj as exponential of minus lambda 1 minus lambda 2 Ej. If I again use the first constraint, that is summation of Aj is equal to A, I will get pretty much the same result that we had earlier, and that gives me exponential of minus lambda 1 is equal to 1 over summation of exponential of minus lambda 2 Ej, and therefore, what I have going back in the expression right here is Aj by summation of Aj is exponential of minus lambda 2 Ej by summation of exponential of minus lambda 2 Ej, and Aj by summation of Aj is simply Aj by A, and now since we have found the most probable distribution, we can call it Aj star, and this becomes the probability of the state J for the most probable distribution, right. So, this again looks like the results of the Boltzmann distribution, but now it applies to system as a whole. So, therefore, if I am now interested in any property m bar, I can write as summation of mj pj, and that is summation of mj exponential of minus lambda 2 Ej by summation of exponential of minus lambda 2 Ej. We will show it later that the lambda 2 has the same meaning as earlier, that is equal to beta, which is 1 over kBt. We will establish that more clearly for the canonical ensemble, and actually we will pretty much derive the zeroth law of thermodynamics in the coming classes. For the time being, just take for granted that lambda 2 is equal to beta. So, therefore, what we have is m bar is summation over mj exponential of minus beta Ej by summation of exponential of minus beta Ej. Now, there is something interesting about what you have in the denominator here. Let me give it a name and see what are the properties of this denominator that makes it very interesting. So, let me call this thing q, which is referred as the partition function. So, the partition function, it comes out to be a very useful concept, is defined as basically the sum over exponential of minus beta Ej. This we can think of as some sort of a Boltzmann factor, because this tells me the probability of having a state Ej with some prefactors. So, essentially if I sum over the Boltzmann factor for all the possible states of the system, what we get is a partition function. Since we are doing it for the canonical ensemble, we can call this the canonical partition function. Now, there is something very interesting about this partition function. First thing you may notice is that since it appears in the denominator right here, what essentially it is doing is somewhat normalizing the probabilities. We know the probabilities are proportional to exponential of minus beta Ej. So, if I take a summation over that, that gives me a normalization of the probabilities. So, basically if I look at e to the power minus beta Ej by q, if the probability is defined as this, then the summation of the Pj for all the possible systems must be equal to 1, which has to be the case because essentially it is summation of E minus beta j and q is already the same number, and also because the probabilities must add to 1, right. So, one use of the partition function is that partition function is a normalization function of probability. The other even more interesting use is that the partition function also happens to be a generating function. And what I mean by the generating function is, if I know the partition function of the system, I can compute a whole host of properties. The other way of saying that is that if I know the partition function, we can find all the properties of the all thermodynamic property of the system, right, and you can see by couple of examples. So, let us say if I start with q as summation of e to the power minus beta Ej. Now, what happens if I do a dou q by dou beta? So, this gives me again a summation over e to the power minus beta Ej multiplied with the derivative of minus beta Ej, that is minus Ej if I take a derivative with respect to beta, and that is minus of Ej e to the power minus beta Ej. Now, if I divide both sides with q, what I have is 1 by q dou q by dou beta, and if I simply write what q is, so q is e to the power minus beta Ej. If you go back the way we have defined our average properties, you may notice that if I simply replace m with E, what we are actually getting right there is the average value of the internal energy, right. So, the E bar can therefore be defined as minus of 1 by q dou q by dou beta, that is minus of dou ln q by dou beta. So, you can see I do not need to know anything else apart from q, because if I know the function form of q, I can find dou ln q by dou beta, and I can basically recover the average energy of the system, and therefore, I call partition function as the generating function. Let us think of something else. So, we know that for a particular state with energy Ej, we can use the thermodynamic expression for that particular state, and what we have is dEj is TdS. So, temperature is constant for all the states minus pressure of that state Pj dV plus summation over j mu j dnj. So, if I am interested in the pressure of the state having energy Ej, the pressure can be defined as the partial derivative of Ej with respect to the volume, of course, for constant S and constant number of molecules of all the species, right. And if I want to find the average of that, it is going to be P bar as summation of Pj exponential of minus beta Ej by summation of exponential of minus beta Ej, which is, there was a minus sign here, which is minus dou Ej by dou V exponential of minus beta Ej divided by summation of exponential of minus beta Ej, and the same expression I can get if I simply do a derivative of the ln q with respect to V. Why is that? Because q is equal to exponential of minus beta j summation. So, dou ln q by dou V is basically 1 by q, that is exponential of minus beta Ej with dou q by dou V in the numerator, which gives me summation of exponential of minus beta Ej with the derivative of beta Ej with respect to V, that will give me minus beta dou Ej by dou V, which we can see that this is equal to beta multiplied with minus of dou Ej by dou V exponential of minus beta Ej divided by exponential of minus beta Ej, which is the same expression I had just obtained for P bar. So, therefore, I can write dou ln q by dou V as beta P bar. So, therefore, if I know q, not only I can find the E bar, the average energy, I can also find the average pressure. So, therefore, we say that the partition function is a generating function. You can extend the idea and take derivative with respect to Nj and find that even the chemical potential can be obtained using the partition function, and what we obtain is the average chemical potential, right. So, once we know the partition function of a system in the ensemble, then we can pretty much get the properties that we are interested in this case energy, pressure and the chemical potential. So, this is the idea that I wanted to present for the canonical ensemble today. In the next lecture, what you will see is, first of all, how can we also define fluctuations apart from the average using the idea of partition function, and then we also will have a closer connection with the part where we said that Lagrange multiplier should be equal to beta. Actually, we will rederive the third law of thermodynamics. So, with that I conclude here. Thank you.